Hello everyone. So today I'm going to talk about ISO. So in this talk I'm going to cover the high-level design of ISO and some of its key implementations. A more detailed explanation can be found in the paper and in our source code repo on GitHub. So now let's get started. So first let's look at what is ISO. So ISO is first practical thread local GC for Java. It implemented and evaluated in a production JVM, OpenJDK. So it solves a 30-year-old problem, which is how to do thread local GC properly for a language that cannot exploit immutability statically. And ISO can also be used or configured as a request-based GC for multi-threaded services. So I'll show you later, it allows for substantial performance wins when workloads are suitable. So before getting down to the details, let's look at the motivation behind this work. So why we develop ISO? Well, GC performance remains a problem, especially for those large-scale request-based web services. Those services are often latency critical and throughput sensitive. And most importantly, some of them having quasi-independent requests, which can be utilized. And what we want to have here is a collector that has high throughput, low latency, and low heap footprint. So how should we do that? Before answering this question, I would like to show you an interesting old result from Java-C. So Java-C is a benchmark in spec JVM, and it was supposed to be GC intensive at that time. However, someone found that if you set a heap size to some certain values, then all of a sudden, the GC cost is barely visible. This was very confusing, and the result was not clear until this heap occupancy graph was generated. So in this graph, the y-axis is the heap volume or live bytes in the heap, and the x-axis is time. So we can see the heap occupancy goes up and down repeatedly. So if you happen to trigger the GC when the heap is almost empty, like those 4 points, then it's not very surprising you're going to see a almost zero cost GC. This looks very nice, and it should be applicable in the request-based workloads, right? But unfortunately, it's not, because in multi-threaded context, thread heap occupancy won't align. So you won't be able to find a plot point where all requests have just finished their requests. So naively triggering a GC when some requests have finished is more likely to interrupt much more threads in the middle of handling requests. And this is disastrous for latency. So it looks like what we really need here is a thread local GC that allows for each individual thread to collect their own garbage without interfering with each other, right? But why no one has done this before? Well, because there's no practical thread local GC for languages like Java. Until now, thread local GC has been limited to languages with statically exploitable immutability. I'll get onto this later, but now let's briefly look at thread local GC. So these are the two papers from PLDI'25, who first designed and implemented a thread local GC for the functional language ML. So they were very old papers. They were published like 30 years ago. So in the simplest case, each thread operates entirely independently with its own private heap. So here's an example. We have two threads, thread A and thread B. So you can see thread A doing a local GC, and thread B is not affected. Similarly, when thread B is doing local GC, thread A is not affected. Right? This looks very nice. But actually, this is not reality, because in practice, some objects will be referenced from globals and thus become public. So what does that mean, or what challenges does that present? Okay, now we introduce public objects and public heap, which contains all the public objects. So they are represented in white circle, and those blue circles are private objects. Since now we have two kinds of objects, we now can have pointers from private to public, but we might also have pointers from public to private. And in this particular case, it's a publication operation, which is problematic for thread A, because it introduced race condition. So how do we deal with publication? Well, PLDI'25 proposed an invariant, what we refer to as the DLG invariant. It reads private objects can only be reached from the stack of the thread that allocated them. This invariant can be enforced by a write barrier that checks for public to private pointer stores. And this invariant has a very important implication. Objects can only be published by their owning thread, which means there won't be any race. So this is a high-level illustration of how to maintain a DLG invariant in the right barrier. So before you install the public to private pointer, you first make all the referenced objects public. And only after doing that, you install the pointer. So great, looks like DLG solved this problem for us. Well, not so fast. There are still issues unresolved. So how do we know all references to moved objects? So far, public objects reside in a distinct heap. So this implies moving objects upon publication, which is problematic. Remember in the previous example, there were pointers from other private objects pointing to the objects that are about to be published. And now, since those objects are moved to the public heap, we need to fix their pointers. Otherwise, we have some dangling pointers. So the literature gives us 3 solutions. The first one is just do a thread local GC at every publication, like this. So similarly, after you copy all the objects to the public heap, then just trigger a local GC, which will fix all the pointers. And only after doing that, you install the pointer, right? But remember, we are talking about write barrier. So do a thread local GC in a write barrier. This sounds crazy, because you might end up doing millions of local GCs, right? And in fact, there are even more reasons why this is not going to work, because in order to trigger a local GC in a write barrier, every pointer store has to be a save point. And none of the production runtime can afford to do this. So the main takeaway here, this is not a solution. So another approach is to exploit statically enforced immutability, like the functional language ML. So if objects are immutable, we can just duplicate them so that public objects will now point to the public copies, while private objects still pointing to the private copies, right? It looks fine. But how do we resolve this without immutability? Because there are many languages like Java which doesn't have this nice property. So we need to find some other solution, right? So there's another solution, or naive solution, I would say. It's just use a non-moving heap. So instead of having public heap and private heaps, we just merge them into one joint non-moving heap, and public-private becomes logical rather than physical. So because no objects will ever be moved, so no pointers needs to be fixed. And similarly, when an object is about to be published, we just need to make sure that all objects referenced are published before the pointers are installed. But unfortunately, non-moving heaps are non-starter. We know they suffer from fragmentation and bad locality. So this is a quick summary of the existing solutions, and unfortunately, none of them is working. So apparently, ISO needs to find some better solution, right? Well, a key insight here is opportunistic copying let us leave public objects in place while moving private objects and vice versa. This solves the referential integrity problem without regressing to a non-moving garbage collector. And this approach is not possible with traditional strictly evacuating collectors such as semispace, G1, and etc. So ISO is built on top of Immix. It uses Immix heap structure and Immix allocator. Apparently, Immix supports opportunistic copying, which is essential. And the bump pointer uses 32 kilobytes blocks and 256 lines. The minimum allocation unit is a single line, so it can fill in holes between live objects. And this is the high level of the heap layout. So there's no separate global heap. Every object has a public bit to indicate whether it has been published or not. And objects living in Immix blocks and public objects, private objects can share the same block. So when thread A is doing a local GC, all private objects are evacuated while public objects are left in place. And after the GC, you can return the free memory. Similarly for thread B, right? And eventually, one might need to trigger a global GC, which in this implementation, we force back to the image. So in the global GC, only public objects are evacuated, while private objects are left in place. And by doing so, we got a more compact heap layout. So now let's quickly look at the evaluation. So this is our experimental setup. We choose 3 request-based workloads with quasi-independence. Our baseline is image, since this implementation falls back to image. We also compared it to G1 to ground the results in the default production GC. So there are a bunch of results in the paper, but at this stage, I just want to focus on the DLG and the publication-related stuff. This is the overhead of dynamically tracking private and versus public. So we can already see there are 3 benchmarks have extremely high overhead. Apparently, ISO is not suitable. And for those 3 benchmarks, although Kafka looks exactly fine, but it turns out to be a single-threaded workload. So there's even an open issue on the couple GitHub. For Cassandra and Tomcat, essentially they didn't do a lot of work, and also Cassandra has relatively high overhead. So this leaves us with Lusearch and Spring, and we also built another compilation server using Spring. We called it Spring JC. So this is the all request time among all those 3 collectors. We can see ISO in the green improves significantly in both Lusearch and Spring JC. While for Spring, ISO is slightly worse than G1, but it is still noticeably better than MX. And this is the median latency, or P50. So the value for Lusearch is so tiny, so it's barely visible here. But we still can see ISO improves noticeably. And this is the P90, very similar to the previous P50 results. All right. So to summarize, ISO is not a general purpose GC. It's targeted large-scale request-based services which having quasi-independent requests. And there are 2 very important insights here. Request-based GC allows for very low overhead collection, and opportunistic copying is the key to first practical thread local GC for Java. So I just want to reiterate that. ISO is just first practical thread local GC for Java implemented and evaluated in a production JVM. And request-based GC for multi-threaded services allows for substantial performance wins if the workloads are suitable. Okay, I'm happy to take questions.
Yeah, so any questions? Please state your name.
Hello, I'm Jung-Yun Kim from KAIST, and thank you for a great talk. And I guess this ISO garbage collector can be, I guess it can be effectively optimize the virtual thread or green thread, for example, in virtual thread in Java or coroutine in Go language.
Yes.
So I'm looking forward to see that, but I'm also not 100% sure whether it will be trivially applied or not, because those kinds of virtual threads is just a user level thread.
Yes,
yeah.
Conceptually, it's relatively simple because there's not much difference between like virtual threads and the current the settings. But for the implementation details, depending on how virtual thread is implemented, there might involve a bunch of work. Actually, we were looking into this a while ago.
I see. Yeah. And I wonder whether the couple benchmark you used has those kind of virtual thread benchmarking.
Not yet, because I believe the virtual thread is only usable in JDK'24. There used to be a relatively issue which will cause deadlock. So in JDK'21, so I think virtual thread hasn't been largely used in the community, I believe.
I see. Thank you.
Yeah.
Okay, maybe you can have Dan switching the computers and no, come on with the one last question.
Tomoharu from University of Tokyo. I have a question about the latency.
Yes.
So your GDC has a surprisingly short latency. Is that latency come from the what garbage collection, or is that come from publication step?
The latency is just the request latency, like how much time it takes a request to start and finish, like the time.
Yeah, so the most significant element that affect to the latency is, so what is the most significant element?
I think it depends. If you go beyond to like P99 and or so, then it's the tail latency, like because we force back to image, so it's GC like contributes a lot. While in the like P50 or P90 below, it's just the mutated time. Most of the time is spent in mutated.
Thank you.
Okay, thanks. Let's thank the speaker again.